All right, let's get right into it. Today, we're basically crashing a university lecture to get to the bottom of some of the biggest buzzwords out there: AI, machine learning, and deep learning. We're going to take what a professor teaches her class and boil it all down into one simple explainer. So grab a seat. Class is officially in session.
So the professor, Dr. Law, she kicks things off with this exact question. She asks every single one of her classes this because, it gets right to the heart of all the confusion. People use these terms like they're the same thing all the time, but they're absolutely not. So let's figure out the answer. But to really get that answer, we've got to zoom out first. We need to look at the big picture, what I like to call the AI family tree. It's all about seeing how these ideas fit together, starting from the very beginning. So way back in the day, what we called AI was really just a super complicated instruction manual. You can think of it as a bunch of if-then rules. Humans, actual people, would sit there and write thousands of lines of code like, if this happens, then do that. The machine was smart, sure, but only because we told it exactly what to do. It couldn't learn a thing on its own. And this is where the entire game changes. Modern AI, which is mostly what we call machine learning, isn't about following rules we wrote. It's about learning the rules for itself. We just throw a ton of data at the machine, and it starts to see patterns and make its own decisions. It learns from experience without us having to handhold it every step of the way. So here's the most important thing to get straight in your head. It's a hierarchy. Artificial intelligence is the big, giant umbrella term for any smart machine. Machine learning is just one way to do AI. And deep learning, that's an even more specific, crazy powerful type of machine learning. They're not different things fighting each other. They're nested inside one another like Russian dolls. Okay, so that idea brings us right back to Dr. Law's original question. If deep learning is just a type of machine learning, what actually makes it deep? Well, it turns out the answer is actually really, really simple. It all comes down to one little number. Here it is. This is the core difference. Both of these methods use something called neural networks, which are kind of inspired by how our brains work, processing information in layers. Now, standard machine learning, let's call it shallow learning, it only uses one or two of these processing layers. And it's great for simpler stuff, like predicting a house price from a few data points. But deep learning, well, it's built for heavy-duty complexity because it uses a lot more layers. And this is it. This is the magic number. The moment a neural network has 3 or more of these hidden layers, we officially call it deep learning. That's the cutoff. That's the whole secret. And having more layers is what lets it understand really complex stuff, like what's in a picture or the nuance in a human voice. Dr. Law has this fantastic analogy for it. She says regular machine learning is like a house with 1 or 2 floors. It's perfectly fine. It gets the job done for everyday life. But deep learning, that's like a skyscraper. It has tons and tons of floors. You need that massive, complex structure to handle much bigger, more complicated tasks. Okay, so we've got the theory down, right? Now let's get into the practical side of things. In a little chat before class, Dr. Law drops some really fascinating and honestly kind of counterintuitive secrets about how data scientists really build these things. I mean, this is a bit of a shocker, right? An AI professor is saying she doesn't want her models to be perfect. She literally tells her students if they get a score in the high 90s, they've probably done something wrong. And that leads to a really interesting question. I mean, seriously, why would you ever aim for a lower grade? It goes against everything we think about science and getting things right. But there's a really, really good reason for it. The reason is a huge problem called overfitting. See, a model that's nearly perfect has pretty much just memorized the answers to the test. It's like a student who knows the answer key for one specific exam, but has no idea how to solve a new problem. So by aiming for something like 80 or 85%, you're actually building a smarter model, one that can generalize what it knows and handle the messy, unpredictable real world. So building a great model isn't about being perfect. It's about being flexible. And a massive part of that comes down to the data you give it in the first place. Dr. Law says one of the most important and most overlooked parts of the whole process is something called feature engineering. And she has another great way of explaining this. Think about building an AI model like you're cooking a meal. All the little bits of data you have, those are your ingredients. Now, you could have 50 different ingredients on the counter, but a great chef knows that the secret is picking just the 5 or 6 that really matter. Feature engineering is just that. It's the art of choosing the most powerful ingredients to get the best tasting dish.
So we've covered the theory, we've touched on the art of building these things, but why does any of this matter to you? Well, because these multi-layered skyscraper models are already running all sorts of things you use every single day. You know when you unlock your phone with your face? Yep, that's deep learning. It has to process thousands of little points on your face in a split second. A simple, shallow model could never handle that. Or how about when you use an app like Gemini to translate something on the fly? You're using a deep learning model. It's not just translating words, it's understanding grammar, context, and slang. That's the kind of complex stuff that needs that deep skyscraper architecture. And of course, the big one, self-driving cars. They rely completely on deep learning. They are constantly taking in this flood of video data, identifying people, other cars, stop signs. That is a job way, way too big for a two-story house model. So let's end this right back where we started, with Dr. Law's main point. This single sentence really just sums it all up perfectly. Both regular machine learning and deep learning use neural networks, but it only gets to be called deep learning when that network has 3 or more hidden layers. Simple as that. And that leaves us with one last big thought to chew on. The huge shift from the old AI to the new AI is that these machines aren't just following our orders anymore. They're learning from our data, our choices, our behavior, which kind of makes you stop and wonder, what exactly are we teaching them? All right, let's get into it. Today, we're going to pull back the curtain on how AI really learns. And I think you'll be surprised to find out that the whole process is a lot more human than you might think. So let's kick things off with a kind of weird question. What on earth could a student's final year project possibly have in common with a super sophisticated artificial intelligence? Well, the answer is pretty much everything. To really get this, let's start with a process that I think we can all understand pretty well. You know how this goes, right? It's that classic cycle. The student submits their first attempt, their first draft. The supervisor then looks it over, points out what's working, what's not, and sends it back with a ton of feedback. Then the student takes that feedback, revises their work, and submits a much, much better version. And this quote right here, it just nails the whole point. The supervisor's job isn't just about correcting typos or fixing grammar. It's about quality control. The real goal is to push that student to understand their topic so deeply that they are ready for any question you could throw at them. It's about building genuine mastery. So what's really fascinating is how this whole idea has a direct parallel in the world of AI. Let's see how this same framework applies to machine learning. And here we are at the most important question. A student has a human expert to guide them, but an AI, it's just code, right? It doesn't have a person sitting there marking its homework with a red pen. So how does it get that crucial feedback? How does it even know when it's wrong? And more importantly, how does it fix itself? Well, it all starts with the AI doing exactly what that student does. It produces a first draft. In the AI world, we call this draft a prediction, and the process is known as forward propagation. Now, don't let the technical name fool you. Forward propagation is really just the AI taking in some information, running it through its own internal logic, and then spitting out its best guess. It's like the AI is saying, okay, based on everything I know so far, here's what I think the answer is. That's its first draft. Let's make this super concrete with a simple example. Imagine an AI that has one job, to answer the question, should you wear a jacket today? To figure this out, it looks at 3 little pieces of data: the temperature, the wind speed, and whether or not it's raining. Now, to make that decision, the AI gives each of those inputs a level of importance or a weight. So, for example, it might decide that rain is twice as important as temperature. It multiplies the inputs by these weights, then adds something called a bias, which is kind of like a thumb on the scale to nudge the result one way or the other. And it comes up with a final answer: a 1 for yes, or a 0 for no. And that is its first draft. But what if that first draft is totally wrong? This is where the real magic happens. This is the AI's version of getting that supervisor feedback. And this process is called backward propagation. You can think of it as the AI's self-correction mechanism. The system takes the AI's prediction, compares it to the actual correct answer, and then measures the difference. That's the error. Then it works backward to figure out what went wrong. And this right here, this is that uh-oh moment.
Let's say the AI predicted 1, meaning you should definitely wear a jacket. But in reality, it was a beautiful sunny day, so the correct answer was 0. The AI made a mistake, and now it has an error to learn from. So what happens next is absolutely the most important part. The AI works backward from its mistake, and it asks, which of my internal weights was most responsible for this screw-up? Did I overvalue how windy it was? Did I undervalue the temperature? It finds the culprit, makes a tiny, tiny adjustment, and then it gets ready to try again. So all of this builds into this incredibly powerful, continuous cycle of improvement, a cycle that mirrors how we humans learn almost perfectly.
I mean, just look at this. When you put them side by side, the similarity is just undeniable. The student submits a draft. The AI makes a prediction. The supervisor gives feedback. The system calculates the error. The student revises. The AI adjusts its weights. It is the exact same iterative loop of trial, feedback, and improvement.
So this is it. This is the fundamental engine of AI learning. Predict, compare, correct. Forward propagation, then backward propagation. It's a simple loop that, when you repeat it millions, even billions of times, allows an AI to go from these clumsy first drafts to outputs that feel like, well, genius. And that leaves us with one final and really critical thought. You know, that student relies on a good supervisor to get quality feedback. The AI, on the other hand, relies completely on the quality of its training data, those correct answers it learns from. So if the very foundation of this whole process is correcting errors based on that data, what happens when the information we feed the AI is incomplete, or biased, or just plain wrong? That technical challenge, making sure the AI's supervisor data is perfect, is really what defines the next frontier of AI.
All right, let's talk about that big, deep learning assignment. I know, it can feel like you're staring up at a huge mountain, but don't sweat it. Today, we're going to give you the map and the gear to conquer it. We're breaking it all down into a super clear, step-by-step plan.
So you've got the assignment brief, you've read it, maybe a couple of times, and you're just feeling overwhelmed? Yeah, you're definitely not alone. But stick with me, because in the next few minutes, we're going to turn that uh-oh feeling into a solid, okay, I got this strategy.
Okay, so here's our game plan. We'll kick things off by understanding the challenge itself. Then we'll dive into Assignment 1, which is all about the research, and then Assignment 2, the hands-on part. After that, we'll cover some must-know tech concepts. And finally, we'll talk about how this isn't just for a grade, it's a real opportunity.
All right, first up, let's get our heads around the big picture. This whole assignment is really a two-part mission. Now, you're going to submit them together, like one big package, but it's super important to remember that each part has its own unique goal.
Okay, so let's break that down. Think of it like this. Assignment 1, that's 40% of your grade, is your reconnaissance mission. You're the detective, a researcher, exploring what's already out there in the world of deep learning. Then you've got Assignment 2. This is the main event, the big one, worth 60%. This is your build phase. You take everything you learned and actually create something. And hey, both of these are individual submissions, so it's all on you to shine.
All right, let's zoom in on Part 1, the literature review. Now, this isn't just about summarizing a bunch of papers. Nope. Think of this as laying the foundation for a skyscraper. It has to be solid, analytical, and it's what your whole project is going to stand on.
And this is maybe the single most important tip for this section. Your professor doesn't want a summary. They really, really don't. They want you to be a critic, a professional critic. Don't just tell them what the paper said. Ask questions. Why did they do it that way? Could this result be better? What did they miss? That's where you're going to get the top marks.
But wait, to be a good critic, you need good material, right? So where do you find it? Simple. Your first stop should always be your university's library portal. That's your golden ticket. And here's a pro tip. Always hit that peer-reviewed filter. That's your quality control. Oh, and if you ever hit one of those annoying paywalls, don't even think about paying. Your librarian is basically a superhero who can get you past it. Use them.
Okay, now for the big one, the main event, Assignment 2. This is where the rubber meets the road. It's worth a whopping 60% of your grade, and it's where you stop just reading about deep learning and start doing deep learning.
Now, let's be super clear on something. Nobody expects you to reinvent the wheel here. You're supposed to stand on the shoulders of giants. So yeah, absolutely modify existing code. Use APIs. Leverage your pre-trained model. That's smart. But, and this is a huge but, what you can't do is just go to GitHub, download a complete project, change the name on it, and turn it in. The key word here is your project. It has to have your fingerprints all over it.
Okay, Data. Your model is nothing without good data, and the rules of the game change depending on what kind of data you're playing with. Working with images, you've got to be using data augmentation. It's not really optional. Trying to predict the stock market? You can't just use last year's data. You need at least 20 years to see the whole picture. And synthetic data? Sure, you can use it, but there's a catch. You have to grow it from a seed of real original data.
And don't forget, this isn't just about the model running in the background. You need a way for people to actually use it. You need a UI. So what's your best bet? Well, if coding isn't your strongest suit, go with Streamlit. Seriously, it's a lifesaver. If you're comfortable with code and want more control, Flask is fantastic. And if you're already a web dev pro, then yeah, Django is the powerhouse you're looking for.
All right, let's shift gears a bit. To really nail Assignment 2, you've got to have a few key technical ideas locked down. Think of this as us packing your toolkit for the job. So first, just a super quick reminder of why we're even using deep learning here. Traditional machine learning, it's awesome for neat, tidy spreadsheets. But you have to be the expert and tell it exactly what columns to look at. Deep learning is different. It's built for the messy stuff, images, sound, text. You just feed it the raw data and it figures out what's important all by itself. It's a game changer. But how does it learn all that complex stuff? The magic ingredient is the activation function. I love this analogy. Without an activation function, your neural network is like an artist who can only use a ruler. Everything is a straight line. Pretty boring, right? An activation function gives the artist a full set of tools to draw curves, swirls, and complex shapes. And the real world is full of curves, not straight lines.
So which one should you use? Well, there's a pretty simple cheat sheet. For all those middle layers, the hidden ones, just use ReLU. It's the standard. It works great. The real decision comes at the very end, at the output. If your model needs to answer yes or no, use Sigmoid. If it needs to pick one thing from a list, like cat, dog, or bird, use Softmax. And if you're just trying to predict a number, like a price, you don't need one at all.
Next up, the optimizer. If your network is the brain, the optimizer is the teacher. It's the algorithm that looks at the network's mistakes and gently adjusts things to help it get better and better. And for this project, you don't need to overthink it. Just use Atom. It's the most popular for a reason. It just works. So how does the teacher, the optimizer, know if the student is making mistakes? It looks at the test score. And that's exactly what the loss function is. It's the test. It gives the model a score on how wrong its prediction was. The whole point of training is for the optimizer to help the model study until that score, the loss, is as low as it can possibly be. Okay, let's take a step back for a second. I really want you to hear this. This assignment is so much more than just something you do for a grade. If you play your cards right, this project can be a serious launchpad for your career. First off, and this is huge, a really good project doesn't just die after you submit it. Think about it. With a bit of extra work, some more polish, this could actually become your first academic publication. How cool would that be? And if that's not enough, this project is basically a cheat code for your capstone. Seriously. That literature review you did for Assignment 1, that's your capstone proposal. Done. The application you built for Assignment 2, that's the heavy lifting for your capstone development. Also done. You're giving your future self a massive gift by doing a great job on this now.
And finally, a little insight into your professor's mindset. When they give you feedback on a draft, their job is to make sure you have everything you need to pass. They're getting you across the finish line. But if you want to win the race, if you want that A, that final push, that extra bit of polish and innovation, that part is all on you.
So there you have it. We've gone over the what, the how, and most importantly, the why. Look, this assignment is tough, no doubt about it. But it's also a massive opportunity. An opportunity to build something you're really proud of, to maybe even get published, and to get a huge head start on your capstone. You have the blueprint now, so the only real question left is, what amazing problem are you going to solve?
You ever wonder what's really going on inside an AI's head when it recommends a movie or a song? Well, today, we're going to tear one apart to see how it works. We're building a simple AI from the ground up to solve one of the most pressing issues of our time. Right? This is the big question. Our goal is to create an AI that gives us a straight-up go or don't go. But to get there, we first have to teach it what's important, what it should even be looking for. All right, first things first. We can't just toss a menu at an AI and expect it to understand. We have to speak its language, and that language is data. And that data comes in the form of what we call features. Now, don't let the jargon fool you. These are just the same things you probably consider. You know the rating, how pricey it is, how far you have to drive, and how long you're going to have to wait. By neatly organizing this stuff into a table, we're giving our AI the exact structured information it needs to get started. Okay, so our data is ready to go. Now it's time for the really cool part, building the brain itself. And no, we're not talking about some sci-fi robot brain. It's actually a pretty elegant, structured model that handles information in a very specific way. The blueprint for our AI is called a sequential model. Sounds complicated, I know, but it's actually super straightforward. It just means we have these layers of artificial neurons kind of stacked on top of each other. Information goes in the front, flows through each layer one by one, and boom, a decision pops out the other end. Simple as that. So what's happening inside each of those little neurons? Well, they use something called an activation function to decide if the information they're getting is important enough to pass along. For all the middle, or hidden layers, we use the industry standard ReLU. Just think of ReLU as the workhorse of the whole operation. It's fast, it's efficient, and it's just really, really good at its job. But when we get to the very last layer, the one that makes the final call, we need a specialist. We're looking for a simple yes or no type of answer, right? So we use the sigmoid function. Its entire purpose in life is to take whatever messy number the network spits out and neatly squeeze it into a probability, a clean number between 0 and 1. It's how we get a nice, understandable percentage at the end. So here's the bottom line. You use different tools for different jobs. ReLU is doing all the heavy lifting and processing inside the brain, while sigmoid is our specialist at the end, giving us that final clean probability. Okay, so we've built the brain. Now how does it actually get smart? We've got the structure, but an empty brain isn't very useful, is it? The real magic of AI is in the learning process. And honestly, it's basically just a massive, super fast cycle of trial and error. The entire learning process, this whole complicated thing, really just boils down to a simple two-step dance that it does over and over again. First, the network makes a guess. We call that forward propagation. Then it looks at how wrong it was and fixes its mistake, and that's called backward propagation. Guess and correct. That's it. Let's break that down a bit. Forward propagation is the thinking part. The restaurant data flows forward through the network, from the inputs, through all those hidden ReLU layers, all the way to the end where it spits out its first guess. And this is where the learning actually happens. The network compares its guess to the real answer, figures out how wrong it was, that's the error, and then sends that error signal backward through the entire network. It's like it's telling every single connection, hey, you were a little bit off, try adjusting this way next time. It's literally learning from its mistakes. So what's steering this whole correction process? A piece of software called an optimizer. We're using the most popular one out there, Adam. You can think of Adam as the teacher in the classroom. It's intelligently guiding the network, telling it how much to adjust its connections so that it learns quickly and efficiently without going haywire. So at the very beginning of training, our network is clueless. It's just making random guesses. And we measure how bad its guesses are with something called a loss score. Think of it like a golf score. You want it to be as low as possible. And right now, yeah, it's really, really high. The model is getting everything wrong. But then we start the training. We show it all our data over and over again in cycles we call epochs. And just look at this timeline. After the first pass, the loss is still pretty bad. But then around epoch 8, you can see it, the aha moment. The loss starts to drop and fast. By the time we hit 200 epochs, it's pretty much figured things out. And this is the result. After 200 cycles of guessing, checking its work, and correcting its mistakes, that loss score has absolutely plummeted to just 0.04. That's an incredibly low error rate. It means our network has officially graduated from a random guesser to a highly accurate predictor. Okay, our AI is trained, it's smart, and it's ready. But now for the moment of truth. Let's see how it handles a restaurant it's never, ever seen before. Let's give it some new data. Here we go. A brand new spot, amazing rating, not too expensive, and the distance and wait time are both pretty reasonable. This is totally new information for our AI. It's time to see what it thinks. The model takes these 4 numbers, they flow through all those trained layers we just built, and at the very end, that sigmoid function does its job. It spits out one single number, 0.75. So what in the world does 0.75 mean? It means there's a 75% probability that, based on all the examples it learned from, this is a restaurant you're gonna like. The AI has made its call. The final verdict is in, and it's a definite go.
Look,
Picking a restaurant is a fun little example, but the process we just walked through, this idea called deep learning, is the engine behind some of the most powerful AI on the planet. So why is it such a big deal?
Well, here's the key difference. The old school machine learning is great with neat, tidy spreadsheets like the one we made. But deep learning thrives on chaos. It loves messy, unstructured data like images, audio, or raw text. We wouldn't need to tell it the restaurant's rating. It could learn to figure out if a restaurant is good just by looking at thousands of photos of the food, all on its own. It learns the important features automatically.
And that really brings us to the final mind-bending thought. We just built an AI that makes a simple choice. But this exact same process, learning from data through layers of neurons, is what allows an AI to spot tumors in medical scans, to drive a car using a video feed, or to translate languages on the fly. It really makes you stop and think, if we can teach it this, what's next?
You hear it all the time, right? Machine learning, neural networks, AI. But have you ever stopped to wonder what that actually means? How does a machine go from knowing literally nothing to making predictions that can feel, well, pretty darn smart? Today, we're going to pull back the curtain and take a journey, step by step, through how a neural network is actually trained.
So let's just dive right in with the big question. How does a machine go from clueless to clever? I promise you, it's not magic. It's a process, and it's actually a lot more intuitive than you might think.
And here it is, the big secret right at the beginning. It learns pretty much the same way we do. Seriously, think about learning to play a new video game. You try something, you fail, you learn, and you adjust your strategy for the next try. That cycle, try, fail, adjust, that is the absolute heart of how machine learning works.
Okay, so every learning journey has to start somewhere. For a brand new, untrained neural network, that first step is making a completely random, uneducated guess. This is what we call the forward pass.
Here's how it works. First, we feed the network some data. Let's say we give it the temperature and the wind speed. That information then flows forward through all the network's internal layers, and on the other side, it spits out a prediction. Since it knows nothing yet, its first guess, like wear a jacket, is basically just a shot in the dark, a total guess.
So, that first guess was almost definitely wrong. But the real question is, how wrong was it? Before the network can learn from its mistake, it needs a way to measure its own failure. It needs a reality check.
This right here, this is the question that drives everything else in machine learning. Because think about it, if you can't put a number on your error, how can you possibly get better in a systematic way? The network needs a score, a hard number that says, hey, you were a little off, or whoa, that was a terrible guess. And the tool for that job is something called a loss function. The easiest way to think of this is as a mistake calculator. It just compares the model's guess to the actual correct answer and spits out a score. We call that score the loss. A high loss means a big mistake. A low loss means it was getting close. The entire goal of training is to make that loss number as tiny as possible.
All right, so the network made a guess, and we calculated exactly how bad that guess was. Now comes the cool part. This is where the actual learning happens, using that failure to get smarter.
And this is so critical to understand. The mistake isn't just a failure to be thrown away. It's a signal. That loss score we just calculated, it becomes the most important piece of information the network has. It's the guide that tells the network exactly how it needs to change. Without the mistake, there's no learning, period.
So how does it use that signal? Through a process called the backward pass, or its more famous name, backpropagation. The network takes that error score and sends it traveling backwards through the whole system. As it goes back, it figures out how much and each and every little connection inside the network contributed to that final mistake. And then it makes a tiny adjustment to each one.
You know, a perfect analogy for this is an assembly line. Imagine the final inspector at the end finds a scratch on the product. She doesn't just yell, "It's wrong," she sends a precise message back down the line. Hey, worker C, your machine needs to be adjusted a tiny bit to the left. Worker B, ease up on the pressure. Each person makes a small tweak, and the next product comes out perfect. That's exactly what backpropagation is doing. Now that whole dance, forward pass, calculate the mistake, backward pass, adjust the connections, that's just one single learning step. To get really good, the network has to do this over and over and over again. We're talking thousands, sometimes millions of times.
But here's the thing. Trying to learn from a ginormous data set all at once would be incredibly slow.
So instead of trying to read the entire library in one go, the network just reads a few books at a time. These small, manageable chunks of data are called batches. The network learns from one batch in every single step.
And when the model has finally worked its way through every single one of those batches, when it has seen all of the training data exactly one time, we call that completing one epoch. Let me make that even clearer.
Let's stick with the reading analogy. If your entire dataset is a book, you don't absorb it all at once. You read it one page at a time. Each one of those pages is a batch. Once you've read every single page and finished the whole book, you've just completed one epoch. Simple as that.
So this is the full training loop. It's this constant rhythm. Process one batch, calculate the mistake, send the error backward to adjust, and then grab the next batch. This cycle just repeats over and over again until it finishes an epoch. And then the whole thing can start all over again for many more epochs, with the network getting just a little bit smarter with every single pass.
Now, we've talked a lot about the training process, but there's one last piece of the puzzle, and frankly, it might be the most important. You can have the best training in the world, but if the network's initial design, its architecture, its blueprint, is wrong for the job, it's all for nothing.
The architecture is everything. You have to match the tool to the task. For instance, if you're analyzing complex medical scans to spot tumors, a basic, simple network is just the wrong tool. It's like trying to perform surgery with a spoon. You need a specialized tool, something like a convolutional neural network, or a CNN, that's literally designed to see and understand patterns in images.
And the difference is just staggering. Look at this. For a cancer detection task, the wrong architecture might get you, say, 60% accuracy. That's not great. Barely better than a coin flip. But the right architecture, the one built for the problem, that can get you up to 95% accuracy or even higher. The blueprint is what makes the real difference.
And this is really the bottom line. No amount of training, no matter how many thousands of epochs you run, can fix a fundamentally flawed blueprint. The architecture itself has to be the right fit for the data and the problem right from the very beginning.
Which leaves us with a final question, one that's useful to think about for any project, really. Is the fundamental design right for the job? Because if it isn't, all the hard work in the world can feel like you're just trying to cut wood with a spoon. Thanks for joining me on this one.
Hey everyone, and welcome. So have you ever wondered how an AI sifts through, literally billions of possibilities to find that one single perfect answer? Well, that's exactly what we're going to break down today. Let's get right into it. So what's the secret? It's actually a pretty cool analogy. Just picture this. You're standing in a massive swimming pool, but it's the middle of the night. It is pitch black. And your job? You have to find the single deepest spot in the entire pool. This little quest, well, that's almost exactly what an AI is doing when it's learning.
All right, so let's talk about this challenge. Your mission is to find that deepest point. In the world of AI, that spot is what we call the best answer. It's the point where the AI makes the fewest mistakes, where its accuracy is highest. That's the whole goal of training a model. Now, this ultimate goal, this deepest spot, it has a fancy name, the global minimum. Think of it as the perfect combination of all the AI's settings and knobs, the one setup that gives you the absolute best result possible. Finding this global minimum isn't just part of the job, it's the entire reason we train an AI in the first place. Okay, but here's the catch. It's totally dark, you can't see anything, you don't have a map, so how on earth do you know which direction is deeper, right? All you can do is rely on what you can feel right there, under your own 2 feet.
And what you feel is the slope of the floor. Is it tilting down? Is it flat? In the world of math and AI, we call this the gradient, and it's your only clue. It tells you which way is the steepest way down from wherever you're standing. For an AI, calculating this gradient is just like feeling the floor to figure out where to take its very next step.
Now, what's really mind-bending is that a perfect map of the whole pool, it does exist, it's just invisible to you. We call it the loss function. This function is basically a complete mathematical description of the problem. It defines the depth at every single point. The deeper the spot, the lower the loss, or the error. The AI's whole goal is to find the lowest point on this map, but, and this is the key, it can never see the whole thing at once. It can only feel that tiny little bit of gradient right where it is.
Okay, so you know which way is down. Great. The next big question is, how do you actually move? Are you going to take tiny, careful little shuffles, or are you going to take a giant leap of faith? This decision is one of the most important ones you make when training an AI, and it's all about setting something called the learning rate. And this lays out the trade-off perfectly.
If you choose a small learning rate, you're taking these tiny, shuffling steps. It's super cautious. You know you won't accidentally step right over the deepest spot. The big problem? Man, it could take a very, very long time to get there. On the flip side, with a large learning rate, you're taking these huge leaps. You move much faster for sure, but you could easily jump clean over the global minimum. You might just end up bouncing from one side of the pool to the other forever without ever finding the bottom.
So getting through this dark pool isn't just a race against time. You also have to watch out for traps. See, the floor of this pool isn't a simple, smooth bowl. No way. It's got all these weird dips and ridges and tricky spots that can totally fool you.
The most common trap you'll find is something called a local minimum. This is like a little divot in the pool floor. When you're standing in it, every direction feels like it's going up. So you think, hey, I did it. I found the bottom. You found a spot with pretty low error, but it's not the lowest possible error. Your AI model is performing okay, but it's stuck when it could have been performing perfectly.
And then there's another sneaky one, a saddle point. Imagine you're standing on some kind of underwater ridge. The floor slopes down in front of you and behind you, but it slopes up to your left and your right. It's like a Pringles chip. The gradient, that slope you feel, is basically zero, which tricks the AI into thinking it's on a flat bottom. It just gets stuck, totally confused about which way to go to keep heading down.
And this brings us to a really crucial point. The difficulty of this whole quest really depends on the shape of the pool, or in AI terms, the landscape of that loss function. Not all problems are created equal, not by a long shot.
To really get this, let's compare two types of pools. Some problems are like a simple, perfect bowl. We call these convex. They've only got one bottom, so no matter where you start, you just head downhill and you're guaranteed to get there. Easy. But most real-world AI problems are more like non-convex water parks. Think about it, a huge, messy landscape with tons of different pools, slides, ridges, and tunnels. It's absolutely filled with those local minimum traps, making the search for the true global minimum an incredibly difficult challenge.
And this is the reality check. Training an AI to recognize your face, or understand what you're saying, or drive a car, that's not like finding the bottom of a simple bowl. It's like being blindfolded in a massive, chaotic water park and being told, okay, find the deepest point somewhere. So, why do we care so much about this quest in the dark? Why does it matter? Well, because this whole process, which we call optimization, is the engine that makes all of modern AI not just possible, but practical and powerful. I mean, just look at this. Without these smart strategies for navigating the pool, trying to train a big AI model would be like wandering around that water park randomly, forever. It could take years and cost millions of dollars in computer time. But with optimization, we can find a great answer in just hours or days, cutting the time and the cost down to a tiny fraction. It's a total game changer.
And this isn't just some abstract theory. This is the tech behind stuff you use every single day. Optimization is how Netflix just knows what show you're going to want to binge next. It's how Google ranks your search results. It's how AI and hospitals can learn to spot diseases on scans better than a human can. It's everywhere.
At the end of the day, optimization is what gives us a system for navigating the darkness. It takes AI from being just a wild guessing game and turns it into an efficient, intelligent search for the best answer. And that's what makes it one of the most important fields in all of computer science.
So, that leaves us with one final thought to chew on. We know the problems we're trying to solve, the really important ones, are these incredibly complex water parks. The challenge of finding that single deepest point is still one of the biggest frontiers in all of AI research. So the real question is, what's the next brilliant strategy we're going to discover to help us navigate the dark?
All right, welcome. Today we're going to break down one of the most core ideas in all of AI, how a model actually learns. And we're going to do it with one simple, super powerful analogy.
Okay, so just picture this. What if training an AI was like trying to find the deepest spot in a huge swimming pool? But it's pitch black. Your mission is to find that one single deepest point. You can't see a thing. All you can do is kind of feel your way around. This right here is basically the challenge an AI is up against during training.
So yeah, let's call this the dark pool problem. The AI has to find the one best solution out of millions, maybe billions of possibilities, but it's doing it almost completely blind.
So you might be asking, how does it even know what best is supposed to be? Well, that's where something called a loss function comes into play. Just think of it like an invisible depth map of the entire pool. It literally has the exact depth for every single point. But here's the catch. The AI can't see the map. It can only measure the depth right where it's standing at that very moment. And that really gets us to the whole point of the exercise. The entire training process is just a big search mission to find that one spot with the lowest possible loss value. You know, the absolute deepest part of the pool. For an AI, lower loss just means a better, more accurate, and way more powerful model. That's the prize.
Okay, so we've got our goal, but we're still stuck in the dark. How does the AI actually move around this invisible landscape? Well, if you can't see, you've got to navigate by feel, right?
And the main tool for doing that is something called the gradient. The gradient is really just the slope of the pool floor right under your feet. It's the AI's only clue, its only piece of local info that tells it which way is down from where it is right now.
Now, knowing which way is downhill is great, but that's only half the battle. The next question is, how big of a step do you take in that direction? And that is decided by a supercritical setting called the learning rate. It's literally just the size of the step the AI decides to take as it follows that slope.
And this is where you run into a really important trade-off. A small learning rate, that's like taking these tiny, super careful steps. It's going to be slower for sure, but it's safer. You're probably not going to step right over the deepest point. On the flip side, a large learning rate is like taking these giant, risky leaps. Yeah, you might get there faster, but you could just as easily overshoot the goal entirely and just end up bouncing back and forth across the deep end without ever landing in it.
But here's where it gets tricky. This dark pool isn't just some simple, perfectly smooth bowl. No, it's a really complex landscape, and it's full of hidden dangers and deceptive little traps that can totally fool our blind navigator.
The most common trap you'll find is called a local minimum. Picture this. You find a little dip in the pool, and from where you're standing, it feels like the bottom. The floor slopes up in every direction. So the AI might just stop there, thinking, hey, I did it. I found the best solution. When the true deepest point, the global minimum, is actually way off somewhere else in the pool. And then there's something even weirder, a saddle point. Imagine you're standing on an underwater ridge, kind of like a Pringles chip. The floor slopes down in front of you and behind you, but it slopes up to your left and right. At that one specific spot, the overall slope, the gradient, feels completely flat. It's zero. So the AI just gets stuck. It has no idea where to go next because it's not at a high point, but it's not at a low point either. It's just stuck.
So all these navigation problems lead to two classic issues in AI. First, there's underfitting. You can think of this as just having really poor navigation skills for any pool. The model is too simple. It's like a swimmer who's just taking random steps and never figures out how to follow the slope. Then you have the opposite problem, overfitting. This is like a swimmer who has memorized the exact sequence of steps for one specific pool, perfectly. But if you put them in any other pool, they're completely lost, because they never learned the general principle of finding the deep end.
So, to get around this super complex terrain, data scientists don't just send the AI out on its own. They use different strategies. You can almost think of it like choosing a specialized search party for the job.
And there are pretty much three main ways they do this. First up is batch. This is like sending out scouts to measure the depth at every single spot in the pool before you take even one step. Your direction will be perfect, but man, is it incredibly slow. Then, at the total opposite end of the spectrum, you have stochastic, or SGD. With this one, you just send a single scout to a random spot, get their report, and take a step right away. It's blazing fast, but your path is going to be really noisy and zigzag all over the place. And then, right in the middle, you've got mini batch. This is the happy medium. You send scouts to a small zone, which gives you a pretty good sense of direction at a decent speed.
And this visual really brings home the core trade-off, doesn't it? With batch, you get super high-quality information that's high accuracy, but the speed is just crawling. With stochastic, you get incredible speed, but the quality of your directional info is pretty low. And then you see mini batch sitting right there in the middle, giving you that practical, balanced blend of both.
And because of that excellent balance, mini batch has really become the workhorse of modern AI. It's pretty much the go-to choice for most real-world deep learning projects. Why? Because it's stable enough and it's fast enough to actually get the job done.
All right, so let's climb out of the pool for a second and bring all this back to how real AI models actually get built. How do developers decide which search party, which strategy to use for their specific project?
Well, the right choice really comes down to the project's constraints. You got to ask, how big is your data set? Are we talking about a small backyard pool or an entire ocean? What about memory? How much scouting gear can your computer actually carry at once? And then there's time.
Do you have minutes to train this thing, or months? And finally, how complex is the problem itself? A simple bowl-shaped pool is a whole different ballgame than a massive water park with all sorts of interconnected pools and slides and tunnels.
And this leads us to maybe the most important takeaway of all. In the real world of building AI, the goal isn't always to find the absolute mathematically perfect answer. The real question isn't which method is the most accurate, it's which one gives me the best value and the most practical solution given the constraints I'm working with.
So when you think about it, if AI models are basically becoming these incredibly sophisticated navigators, charting courses through these complex, invisible landscapes to find solutions, it really makes you wonder, right? What new, even more complicated landscapes? I'm talking about things like drug discovery or climate modeling. What new water parks are they just now beginning to explore for us?
All right, let's get right into it. When you're training an AI, it's kind of like a Goldilocks story. You don't want a model that's too simple, and you definitely don't want one that's too complicated. You're looking for that sweet spot, the one that's just right. But as you can probably guess, finding that perfect balance, yeah, that's one of the toughest nuts to crack in the entire world of machine learning.
So to really get a handle on this, let's step away from all the code and the data for a second and walk into a kitchen. Because believe it or not, the difference between a truly great chef and a terrible one is the perfect way to understand the biggest problems we run into when we're trying to build an AI.
Okay, so picture two chefs. First, you've got the undertrained guy. He really only knows how to make like one basic pasta dish. That's it. He can't adapt, can't improvise, he's stuck. In the AI world, we call this underfitting. Then you've got the other chef. She is a walking encyclopedia of recipes. She has memorized everything perfectly. But here's the catch. If you ask her to use a little less salt or the kitchen is out of one ingredient, she completely freezes up. This is overfitting. See the problem? Neither of them is actually a good chef. And that right there, that's the heart of the problem. It's what we call AI's learning dilemma. This constant tug of war to make sure our models don't end up like one of those two failed chefs. What we're really aiming for is a good fit model. This is like a truly great chef who doesn't just memorize recipes. They understand the principles of flavor, texture, and heat. They can improvise. They can create something amazing, even with ingredients they've never seen before. That's the kind of flexible, adaptable intelligence we want in our AI. And to get to that good fit, you have to understand this constant balancing act that's going on under the hood. It's a battle between two fundamental competing forces, something we call bias and something we call variance. So, what on earth are bias and variance? Let's break this down, because if you can really wrap your head around these two concepts, you've unlocked the key to the whole thing. Bias is actually pretty straightforward. Think of it as being consistently wrong, always in the same direction. It's like having a broken bathroom scale that always, no matter what, adds an extra 5 kilograms. It's wrong, but it's predictably wrong. That's high bias. Now, variance. Variance is the total opposite. It's being inconsistently wrong. Imagine a different faulty scale. This one is just haywire. You step on it, it says 55 kilos. You step on it again a second later, it says 70. The next time it's 62. The predictions are all over the map. They're chaotic. That's high variance. Okay, so you've got these two ways of being wrong, the consistent, predictable error and the chaotic, all over the place error. So the big question is, how do these two things, bias and variance, actually come together and mess with an AI's performance out in the real world? A dartboard is the perfect way to see this. Look at that first row. High bias, low variance. Your darts are all clumped together, so you're consistent, but you're way off the bullseye. That's our undertrained chef. That's underfitting. Now the opposite. Low bias, high variance. Here, the darts are scattered all around the bullseye. The average is about right, but any single throw is unpredictable. That's our over-memorizing chef. That's overfitting. The worst of both worlds, of course, is high bias and high variance. You're inaccurate and inconsistent. What we want, the holy grail, is that bottom row. Low bias and low variance. Every shot is clustered tightly, right on the bullseye. That's our ideal model. Okay, that makes sense. We know the different ways a model can go wrong. But how do you know which problem you have? How do you actually diagnose your model when it's sick? To play doctor, you need two things. Just think about it like you're a student getting ready for a big exam. The training data, that's your textbook and all your study notes. It's the material the AI gets to learn from. But then you have the validation data. This is the surprise practice test. It's full of new questions the AI has never seen before, and it's the only way to know if it really gets the material.
And in this world, we measure how well the student is doing using something called loss. It sounds technical, but loss is just a word for mistakes or errors. So low loss is great, high loss is bad. Simple. Training loss is how many mistakes the model makes on its textbook material, and validation loss is how many mistakes it makes on that all-important practice test. And this right here, this is the smoking gun. This is how you catch overfitting red-handed. Look at that tiny training loss. The model is absolutely crushing its study material, right? But then, look at the validation loss. It's through the roof. It's totally bombing the practice test. That huge gap between the two bars, that's your siren going off. It's screaming at you that your model didn't actually learn anything. It just memorized the answers.
Let's look at this with some hard numbers. Scenario A. Training and test scores are both really high and they're super close together. Perfect. That's a good fit. Scenario B. Both scores are pretty bad. The model just didn't get it. Classic underfitting. But now, look at scenario C. A whopping 98% on the training data. Looks amazing, right? But then it completely tanks on the test data, dropping to 70%. You see that huge drop-off? That is textbook overfitting.
So now we know how to spot the problem. We can make a diagnosis. The next big question is, what's the cure? Well, that brings us to one of the most powerful and frankly elegant solutions out there, a technique called early stopping. And the logic behind it is actually really simple. If we know that training a model for too long is what causes it to start memorizing and overfitting, then the whole game is about figuring out the exact right moment to tell it to stop. And the solution is beautiful because it's so straightforward. We literally just stop early. It's a technique called early stopping, and it's all about pulling the plug right when the model hits its peak performance. It works in 3 easy steps. First, you monitor. While the model is training, you're constantly giving it that practice test. You're checking its validation loss. Second, you watch. You're looking for one specific moment, the point where the score on that practice test stops getting better and actually starts to get a little bit worse. And third, the second you see that happen, you stop. You halt everything. You found the perfect point right before it started to overfit. And the reason this works so well is that it's laser focused on that key signal we talked about. That gap between training and validation loss, that's everything. The moment the validation loss starts to creep up, that gap starts to widen, early stopping just nips it in the bud, right then and there. This whole approach is just incredibly effective. It finds that just right Goldilocks sweet spot. It stops the model from getting bogged down memorizing all the weird quirks and noise in the training data, and because of that, the model becomes much, much better at generalizing to new problems it's never seen before. Oh, and bonus, you stop wasting time and computer power on training that's actually making your model worse. So let's go back to our student one last time. Early stopping is basically the wisdom to know when you're done studying. It's realizing you've truly grasped the concepts, and that any more cramming will just lead you to you mindlessly memorizing answers without really understanding them. So it's pretty wild when you think about it. To build the most intelligent systems, one of the most important things we have to teach them is when to stop learning, which kind of leaves us with a bigger question to chew on, doesn't it? If the smartest AI is the one that knows when to stop, what can the rest of us learn from that? Welcome to The Explainer, where we break down big topics. Okay, let's just dive right in. Have you ever stopped to wonder, can an AI actually get too smart for its own good? You know, it sounds like a totally strange question, right? But what happens when an AI stops actually learning and starts just memorizing? What happens when it gets so perfect on the data it's already seen that it becomes completely useless on anything new? And this right here, this is the absolute core of a massive challenge in AI we call overfitting. It's the difference between acing a test because you memorize the answer key versus actually getting the subject. One approach is brittle, but the other one? That one's robust. An overfit model is kind of like a student who has memorized every single question from last year's exam. I mean, sure, they'll get a perfect score on that specific test, but you put a new exam in front of them, one that covers the same ideas but asks different questions, and they're completely lost. And you've got to understand the stakes here can be incredibly high. This isn't just some academic problem. Think about a medical setting.
An AI trained to spot pneumonia might just end up memorizing the specific x-rays it was trained on. So when it sees a new patient scan, it can fail completely. And that could lead to a really dangerous misdiagnosis.
So, how do we stop this from happening? How do we build an AI that genuinely learns instead of just memorizing? Well, the first and maybe most intuitive solution is a technique called early stopping. And really, it's all about knowing when to quit. The idea is brilliantly simple, but so powerful. You stop training the model the very moment its performance on new data, what we call a validation set, stops getting better. You see, that's the point of diminishing returns. Any more studying after that just leads to harmful memorization.
Okay, so here's how it actually works. The model trains for one cycle, we call that an epoch, and then boom, we immediately test it on new data to check its validation loss. That's just a fancy way of scoring how many mistakes it's making. So is that error score still going down? Awesome, we keep training. But if the error starts to climb, a little patience counter starts ticking.
And that counter is so important. We don't just stop after one bad cycle. That'd be too hasty. A patience of 5, for instance, means we're going to wait for 5 straight training rounds with 0 improvement before we pull the plug. It's a great way to prevent us from stopping too early just because of some random little dip in performance. Now, our next solution, it takes a totally different approach to building a more robust model. It's a really fascinating technique, and it's called dropout. I want you to imagine a sports team that relies completely on its one-star player. If that player gets injured, what happens? The whole team just falls apart. Well, that's a model without dropout. Dropout is more like randomly benching different players during practice. It forces the rest of the team to figure out how to work together and become way more resilient, so they don't depend on any single person. So in an AI's neural network, the players are the neurons. With the dropout technique, we randomly bench some of these neurons during each round of training. We just temporarily switch them off. This makes it impossible for any single neuron to become that star player that the entire network starts to over-rely on. What this does is it forces the network to find lots of different paths to the right answer. It builds a much more distributed and robust understanding of the data. Usually, you'll see a dropout rate somewhere between 20 to 50%, which means in any given training cycle, that many neurons are just temporarily sitting on the sidelines. So early stopping and dropout are definitely 2 of the heavy hitters, but the toolkit for fighting overfitting is even bigger than that. Let's take a look at 2 more techniques called L1 and L2 regularization. Let's use an analogy here. Think about managing company costs. L2 regularization, that's like giving every single employee a small pay cut. It reduces the importance of all the connections in the network, but it keeps them all around. This is a great move when you think most of your data features are at least a little bit useful. L1, on the other hand, well, it's a bit more ruthless. It's like firing the least productive employees. It just completely eliminates the weakest connections, setting them to 0, forcing the model to focus only on the strongest signals. The real power here is that L1 simplifies the model and helps you figure out which inputs are just distracting noise. So you choose L2 when you want to tone everything down, and L1 when you really need to clean house. Okay, so what's the big picture here? What's the main thing you should take away from this whole explainer? Well, the goal of training an AI isn't just to make it powerful on paper. It's to make it reliable and, most importantly, able to generalize its knowledge. We want it to work not just in the clean, perfect lab environment of its training data, but out in the messy, unpredictable real world. Techniques like early stopping, dropout, and regularization, they're like the discipline that prevents a brilliant AI from becoming a brittle one. They are the guardrails that make sure the model is learning true patterns instead of just memorizing a bunch of noise. And that really leaves us with a final thought. Maybe true intelligence, whether we're talking about humans or machines, is less about knowing everything and more about knowing what not to overthink.
Welcome to The Explainer. Today, we're diving into something pretty wild. How does a computer actually learn to recognize what's in a picture? The secret lies inside a special kind of AI called a convolutional neural network, or CNN. Let's break it down.
So let's start with a question that seems super simple on the surface. We look at this picture and boom, our brains instantly know it's a cat. Easy, right? Well, for a computer, it is anything but simple. So how does it get there?
Because here's the thing, a computer doesn't see a cat. It doesn't see fluff or whiskers or ears. It sees this, a giant grid of numbers. Each number just represents the brightness of a single pixel. A tiny 28 by 28 pixel image is a grid of 784 numbers.
How on earth do you get cat from that?
Okay, so you might be thinking, why not just feed all those numbers into a standard AI? Well, the problem is a traditional network would take that grid and just flatten it. It turns it into one long, single-file line of numbers. And in that process, all the spatial information, which pixels are next to which, is completely lost. It's like trying to solve a jigsaw puzzle after you've tossed all the pieces in a blender. It just doesn't work.
So to solve this puzzle, we need a specialized tool. And that's where the convolutional neural network comes into play. Its secret weapon, the absolute key to making this work, is something called a filter.
I want you to think of a filter, sometimes it's called a kernel, as a tiny little detective with a magnifying glass. It's just a small grid of numbers, maybe 3 by 3, and its entire job is to slide across the image looking for one and only one specific clue, like a vertical line or a little curve or a certain texture. And you can have a whole team of these little detectives. You've got one that's an expert at finding vertical edges. Another one is a pro at spotting horizontal lines. You can even have filters that blur the image or the exact opposite and sharpen it. Each one is a specialist, totally focused on finding its single pattern.
So what happens when one of these filters scans the image? It produces something called a feature map. And you can think of this map as the detective's final report. It's basically a new image that lights up everywhere the filter found its specific pattern. It's a map of all the clues.
Okay, finding these basic patterns is a fantastic start, but now the network has like dozens of these feature maps. It's a lot of information. The next big job is to cut through all that noise and find the real signal.
And it does this with a really elegant, repeatable process. We call it a CNN block, and it's got 3 main steps. First is convolution, that's applying the filters. Second is activation, to clean up the maps. And third is pooling, to shrink them down. And this whole block can be stacked again and again.
Let's zoom in on that second step, activation. So after we find all these features, the network runs a special function on them. A really popular one is called reload. All it does, really, is go through the feature map and throw away any negative numbers. The effect is that it makes the important stuff, the positive signals, pop even more. It's like cranking up the contrast on the most important clues.
But wait a second. Even after that, these feature maps are still gigantic. We're still dealing with a mountain of data. So the big question is, how does the network shrink everything down without throwing away the good stuff?
The answer is super clever. It's called pooling. Basically, the network takes a small chunk of the map, like a little 2x2 square, and boils it down to just one number. Max pooling is really common. It just looks at that square and keeps the biggest number, the strongest signal. Average pooling takes the average instead, which is great for getting the general vibe of a texture. Either way, the result is a much smaller, more manageable map.
So the image gets put through this whole pipeline: convolution, activation, pooling, not just once, but multiple times. And each time it goes through, it's getting less like raw pixels and more like a rich, abstract map of features. So now, let's see how this all comes together for the final decision.
All right, let's trace the entire path from start to finish. We begin with our image. It hits the first CNN block, where maybe 32 filters are looking for really simple things, basic edges, curves. Then, the output of that goes into a second block, this time with 64 filters, which start combining those simple lines into more complex shapes. You know, things that might be an eye or an ear. After a few rounds of this, the final high-level feature maps are flattened out into one long list. And that list is finally fed to a standard neural network that makes the final call, yep, that's a cat.
Now what's really cool is that none of this is set in stone. A developer can go in and tweak all sorts of things, like how many filters to use or how big they are, and it can totally change how well the AI performs. It's all about finding that perfect balance.
Let's take the number of filters, for instance. The more filters you have, the more patterns the network can learn, right? Which usually means better accuracy. But there's a catch. Every single filter you add makes the network more complex, and it takes way longer to train. If you go overboard, like with 128 filters here, you risk overfitting. That's where the model basically just memorizes the training pictures instead of actually learning what a cat looks like in general.
So, is there a magic number? Well, not exactly, but the source material we're looking at suggests there's a definite sweet spot for a lot of common problems, and it's right around here, between 32 and 64 filters. That seems to be the best bang for your buck, balancing power and efficiency.
And it's not just the number of filters. Their size matters a ton too. Think of it this way. Small 3x3 filters are like having a magnifying glass. They're amazing for spotting tiny details, the texture of fur, a sharp edge.
But larger filters, like a 7x7, are more like stepping back to see the big picture. They're better for capturing the overall shape of an object. And you know what? The best networks usually use a mix of both.
And all of this leads to a really, really important point. A CNN is a phenomenal pattern-matching machine. It gets incredibly good at finding the statistical links between a bunch of pixels and the word cat. But, and this is a big but, it doesn't understand what a cat is. It doesn't know about being fluffy or purring or chasing laser pointers. It's not about meaning. It's all about the math and the patterns in the numbers.
And that leaves us with a really mind-bending thought to end on. If a CNN is just a master at finding patterns in a grid, what else could it see? It's not just about images. You can turn sound waves into a grid, or financial data, or even language. Anything that can be represented as a structured grid is a whole new world just waiting for a CNN to come in and find its hidden patterns.